how they generate a class called Discrete Systems.
Yep, so hi again. Today I'm going to talk about something completely unrelated to what I did yesterday. I will talk about automata. So just to make it clear, automata, we consider that automata are systems that take inputs, process the input, change their internal state, and then produce an output. And automata can be wired together to make bigger automata. So that's just basic things about automata. What I will focus on is memory. So the state space of an automaton will be considered as its memory, its life experience in a sense. And the question is, what happens when the memory of the automata is lost? So actually, when the automaton doesn't have memory in a sense, it becomes what we call reactive, in the sense that it takes an input and only produces an output without changing its internal state. This will be made formal later. The question is, what are the links between automata without memory and general automata? Most of this talk and most of this paper is based on previous work by David Spivak on steady states. He introduced formalism for talking about automata, which he called discrete systems. And in the rest of this talk, I will speak of discrete systems instead of automata. So let's introduce the formalism. We start with type finite sets, which will be a pair of a set and then a function from this set to the category of sets. So this is really just a formalism for a list of sets. And just as traditional lists, okay, I need to target there. Just as normal lists, you can concatenate them. And you can also have, oh, sorry, I have an example. Well, so maybe if you are familiar with the formalism of lists, you can just, it's just the same formalism. You have a function from a finite set to that generates just a list of sets. And then you have functions between lists that will be just a means to transform a list into another, or rather a way to formalize the fact that you take one list and you reorder some objects, you ignore some objects, or you duplicate some objects, and then you get another list. So another example for if you have this list, how can you make it from this list? Well, you just take the A, you duplicate it 3 times, and you take the B and you put it at the end. Also, I leave you think about this problem. Why is there no way to transform this list into this one? It's because there's no C in the second list. So that makes a category of type finite sets and type functions. And that category is symmetric monoidal for the concatenation, not symmetric, yes, symmetric for the concatenation operation. With that monoidal category comes lax monoidal functor, or natural lax monoidal functor, which is just you have a list of sets and you make the product of them. Okay, so for the rest of this talk, I didn't pronounce it, but I will drop the sets prefix, and instead of mentioning the whole type finite set, I would just mention the set of indices. So now we come to boxes. So a box is really just a pair of lists. One of the lists is the input ports of the box, and the second list is just the output ports of the box. Okay, that's what I said. And just as lists, you can concatenate boxes. And you also have what we call wiring diagrams, which are just a way to wire boxes in order to transform a box into another box. So here's a simple example, and here's a sexier example of wiring. And that makes another symmetric monoidal category of boxes and wiring diagram. And the dependent product from before can also be translated into boxes, while you just turn a pair of lists into a pair of products of sets. So for now, boxes are really just empty frames that, in spite of their fractal-like nesting, like you can nest boxes, and that makes like a fractal structure of boxes. They are still empty, and we need to put something inside to make it more, alive. And that's discrete system you put inside the box. So this is the equivalent of automata I was mentioning before. So just a discrete system will be a set of states, a state set, a readout function that processes the state space, that processes the current state and returns an output, an update function that takes an input and the current state and returns another state, and an initial state to make things right. And for a given box, we denote by ds of x the set of all discrete systems that live inside the box, and that makes a lax monoidal functor from boxes to sets. So the talk is about like memory of discrete systems. So actually the question is, discrete systems are very, very general, systems. So the question is, can we find a subset of those discrete systems that generate all discrete systems? And sorry about that, but the title of the presentation spoils the fun. Spoils that question. We are considering memoryless systems that are discrete systems such that, in a way, the state space really doesn't matter. Well, the state space is directly the output of the automaton. The readout function is simply the identity function, and the update function only takes into account the input and just forgets about everything it has seen before. So just as before, we define a mapping, dsml of x, that takes a box and returns all the memoryless systems that live inside. And unfortunately, this mapping is too incomplete to be a functor. So how do we cure this? We cure this by using the notion of closure. So you take a monoidal functor and you take an incomplete mapping that is contained inside in the sense of category of sets. And then the closure of the incomplete mapping will be the smallest lax monoidal subfunctor of A that contains the incomplete mapping. And so, what it really does is, in the case of discrete systems, you take a memoryless system and then you wire it you take discrete memoryless systems, you wire them in any way possible, and you see what you get. And what you get is that the memoryless systems, the closure of memoryless systems gives discrete systems. So the interpretation is that memoryless systems, when wired together, gives you all the discrete systems. And another interpretation that comes from the proof we give, which is constructive, is that, well, to need a state space and to initiate memory, all you need is just the last output and not necessarily the whole list of previous inputs, previous inputs. And well, that's about it. So yes, this theorem is like a generalization of, well, you plug the transistors together and then you get a computer, or you put cells together and then you get whatever complex animal you want. The other more corny conclusion would be that memory emerges from connections, which is actually the case in that proof. And as perspectives, well, the fact is that memoryless systems are quite a big class of discrete systems, so maybe we would find a smaller class that also generates discrete systems. And that's it. Merci pour votre attention.
Okay. Yeah, we have a couple minutes for questions.
Whoa.
Let's go with Jean first.
I don't really get how memoryless systems, how you stick them together and get to simulate a system with memory. So is the idea that information keeps sort of traveling around?
Yeah, that's it. It's really just about feedback. When you allow feedback, you allow memory to emerge. That's it.
Is it wrong to think of the definition of memoryless as really defining systems that can remember one thing for one time step, but no more?
Yes.
That's right.
Yeah, that's right.
Super. You have no past memory. You just remember what you just got.
Yeah, just one time step.
What did you say? Okay.
Yeah, so my question was, why represent a set value function as a list? Was that used here somewhere?
Oh, okay. Okay, please say it again. I think I misunderstood
Why
you.
represent a set valued function as a list?
Yeah.
A set. Was that used here in this talk?
Oh, in fact, the list was the list of input ports of, well, it becomes a list of input ports of boxes. And what the automaton uses is not the list, but the product of the objects of the list.
But don't you have to then like always work up to permutation?
When he says list, he means unordered list.
Oh, unordered list.
Oh, yeah. No, they are finite sets, so finite sets are always ordered. So.
I think that's enough questions. Thank you very much again.
I have to force category theory on engineers, so I don't know if it's harder to force power systems on applied category theorists, but we'll find out. And I just want to give a shout out here to John Nolan. He's an undergrad who was working with the NIST crew before I even got there, but he's kind of done a lot of the work on this project, and he's a really bright kid, just applying to grad school, knows a bunch of category theory and scientific programming. So yeah, okay, here's the government disclaimer. Even though we like and use these things, it's not officially endorsed by NIST. Yeah, so power systems.